Okay, we are going to move fast, but if I get ahead of you in the calculations, just pause. We're going to be doing buffer problems here for the next couple of lectures. So you determine the pH of a buffer made by combining 50 mils of 0.45 molar HF and 40 mils of 0.35 molar NaF. And that breaks up into Na plus and F minus. This is the conjugate base of the HF. So this is all we're interested in, is that F minus. But since we're combining things, we're mixing them together. If you mix, then you have to convert to moles. You have to do that because by mixing two solutions together, you're changing the concentrations of both. So we're going to convert to moles and then divide by the new volume. So anytime there's any mixing involved, either by they'll say combining or mixing or titrating, you're going to have to convert to moles. So what we do is, we have 50 mils, we have to change to liters because we have 0.45 moles per liter, so I'm always going to take this capital M and change it into moles per liter so you can see the math involved, the canceling of units. 40 mils becomes 0.04 liters, always going to have to change to liters, and that's F minus. That's the sodium fluoride, but we leave the sodium off because it doesn't do anything. And in our final equation, we're not going to have the sodium involved. So you can leave it in there if you want. It's just going to, but you should be aware that that's all that we're interested in. Now we have the moles of HF and F minus. This is the moles of HF that were present in the one sample. Here's the moles of F minus present in the second sample. Now the total volume is 50 mils plus 40 mils, which is 90 mils, which is 0.09 liters. So by diluting or mixing these together, both solutions together, we've diluted both concentrations. So we take our moles that are now both part of the same solution and we divide by the volume of this new solution. And this is 0.25 molar HF, and this is 0.156 molar F minus. Okay, so we change to moles, we find the new volume, we divide by the new volume. Now here are our new concentrations that have been diluted by mixing them. They're both species are now present in the same solution. Since they're both in the same solution, we can use them in the same equation, the same Ka expression. Here's our F minus, here's our HF. So this is really a common ion problem. It's just that because we're interested in what its properties are, what it's able to do, what a buffer is able to do when you add an acid or a base, we give it a special name, but it's just common ions that are present here. Let's see, or a common ion between the salt and HF. So 0 minus X plus X plus X, 0.25. The approximation, for my exams, the approximation will always hold for the buffers. You should double check during the exam just to make sure I haven't messed up. But I won't have a buffer problem where where the approximation won't hold, because that would be, you already have enough to worry about. This is the Ka for HF. Approximation holds, so X, which is going to be the concentration of H3O plus, is equal to 0.00109 molar, and the pH is the negative log of that, and that is 2.96. Okay. So fast, but all I've done is I did out all of the math beforehand. So it's just I don't have to tap everything into the calculator, but I didn't skip any steps. So it's all there. Let's try another one. Now this is a base and it's conjugate acid, so and the NH4 or the ammonium nitrate breaks up into ammonium ion and nitrate ion. The nitrate does nothing. This is the one that we're after. We have the ammonia and its conjugate acid. So we're going to determine the new concentration and then plug them both into the Kb expression for ammonia to determine the pH. So we have to do this out. We have the volume and concentration of ammonia, the volume and concentration of the ammonium nitrate. This is the same concentration for the ammonium on its own. It's 2.5 molar. We're going to convert to moles and then divide by the new volume, which happens to be 90 again, 90 mils again. But that's just by chance, can be anything. We do this out. This will give us moles of ammonia, and then we have 30 mils, or 0.03 liters of 2.5 moles per liter ammonium ion. I'm not going to put the nitrate on there. You can certainly keep it in there, but at the end you'll have to show that it breaks up into this ion, so might as well do it now, because we don't carry the nitrate through for that last calculation. It's a counter ion. It's important to be there. To be the counter charge to the ammonia, so that ammonium, so that you have a stable ionic compound. But when it goes into solution, the nitrate doesn't help or hurt us. It just is there as a spectator ion. So now that we know the moles, we divide by the volume, the new volume, which is 0.06 liters plus 0.03 liters gives us 0.09 liters. And then we have the moles of ammonium ion over the new volume. And this is 1.13. When you do it without having to punch all this stuff into the calculator, it goes a lot faster. But I'm following all the steps. You're just not waiting around for me to do the math. And if you're trying to do this as you go, then of course pause it. Try to get us ahead, and then you can replay it again, or start it up again, and you have all the power to go back and forth through this calculation. Now we put in our concentrations into the into this expression. It's for ammonia, so it's Kb expression. So we need to know the Kb for ammonia. That's in our list. That's why we do this. We could certainly have done it as a Ka expression for NH4 plus. No problem there, except that we would have to determine Ka for ammonium ion, which we've done before. But since we have both ammonia and ammonium ion, we choose to do the Kb expression for ammonia, so we set it up in this form. Makes our life much easier, because we can just take the number directly from the table. Now the approximation does hold. You can double check it to be sure, but it definitely does. X is the concentration of OH minus. Be careful with that. We're dealing with a base here. So if you take the negative log of this number, of this concentration, we end up with 4.61, which is POH. We wanted pH. So be careful. I could ask for pH or POH. Could even ask for the concentration of H3O plus if I wanted to here, because you can convert that, but usually it's going to be pH. And that's it.